Thanks very much for the invitation. It's a pleasure for me to talk here. So I think the audience is very mixed. So you should just interrupt whenever you think you have to interrupt me and ask questions. So I want to start with a representation theoretic motivation. And so I'm a least theorist, so I would just start with infinite dimensional Lie representations. No, with infinite dimensional representations of Lie, right? Okay, so complex symmetry, right? So you think we know everything. To some extent this is true, and to some extent this is totally wrong. So in particular, what we know is this KDO, Hausdorff representations, and we know blocks in there, and we might also look at parabolic versions of it. So these are highest rate representations, infinite dimensional, with a locally finite condition with respect to a parabolic. So this is what one looks at. For instance, so these are nice abelian categories of finite global dimension with enough projectives. So one might ask the question, what is the endomorphism then of the direct sum of all projective maps? So these are the indecomposable projectives. I would like to know this. And knowing means precise and the algebra as good as possible. And also, this is the highest rate maybe. So one has kind of Lerner modulus, and I would like to look at the X algebra of Lerner modulus, the direct sum of n lambda, these two direct sum of n lambda, sum over lambda, and these are the Lerner modulus. So some kind of universal highest rate modulus, and so we would like to know this. So, for those who don't know these categories at all, these guys are exceptional objects. So they form an exceptional sequence. And so by this I just mean, when I look at x from n lambda to itself, then this is just C, so I do everything over C. So I just have Homs, the obvious Homs, and I have no higher X.
X is X1?
No, X is all X.
All
X. Yes, here also all X. And I don't put a dot because I need a dot later. If I take again all X from n lambda to n mu, so this exception means that I have a natural ordering on these lambda mu's. For these theory people, this is just a natural ordering on weights, on highest weights. I have only X if lambda is smaller than okay.
Could I follow up on the last question, which is,
sure.
he was noticing if you have Hom, and it looks like that would be one-dimensional.
Yeah, so here I have only something X in X0, which is Hom, and this gives a C, and it has nothing else. That's the same.
Okay. So X is
X
including
is
the graded.
Yeah, it's graded, so X is
the right Hom is C.
Yeah.
You can just write Hom in this audience.
Okay, good. So now, first thing one might ask is, what is the dimension of it? And this is already in this very, very classical setup, highly non-trivial. So on this side, this is parabolic plus analytic polynomials, depending on what the choice of the category. And so this is, I would say, something which is not trivial. And on the other side, here, that's right. So let me put it there, but this is refers to E, and so this is for A, and this is for E. There's a very famous conjecture, which is called the Gaga-Joseph conjecture from the 70s. That the dimension is given by certain R polynomials. So these are nice polynomials, which sometimes are used to define Cassianistic polynomials when you do it somehow combinatorially, maybe not from a Lie theory setup or not from a Cox setup. So these are very famous polynomials. But this turned out to be wrong. So the first counterexample was given, I think, by Bo, and it's just wrong. And so one didn't know anything what the dimension is of this thing. And so what one can prove is that the dimension is given by a certain R-prime polynomials. They have a recursive definition, which is not too complicated, and this can be proved. But in contrast to these R polynomials, which can be used to count the number of points in a certain variety, which comes later over a finite field, these R prime polynomials, I don't know any sort of geometric interpretation. I really would like to understand why these guys come up when we do this. And so this is behind some of the things of the talk. So and then another thing which is important, of course, both P lambdas and N lambdas generate the derived category. Of my given the Boolean category. And so then I take X and now put a big dot. So that's the G version of X. And I take G modules over this. Then this recovers the derived category. Or you want, you can also take A infinity. And so, of course, this is just the classical setup. We can ask similar questions for instance, representations of supergroups. So, like GLMN. So, for instance, I'm interested in integral representation, finite dimensional representation of these supergroups, or if you want modular representation theory. So that's the sort of motivation we got. And now I want to start with this thing, because here I maybe should just mention it, the sort of complexity. If one wants to understand this endomorphism algebra, there's lots of theory which was already developed. So in the case of ordinary category O, or this O0, circle bimodules were introduced exactly, or circle modules to describe this. And this is something which is not trivial. For the parabolic version, circle modules don't work, can't be controlled. But one knows that these KLR algebras, or cyclotomic versions of it, can describe this endomorphism ring. But in practice, you have a description, but you might not be able to really understand, for instance, what is the dimension of this description. So, just to give a flavor of it. So, now I want to start with this side. So what comes out is some kind of directed algebra, and I want to understand this algebra or construct it by general construction using, maybe I call it Morse theory. I put it in quotation marks because I'm not 100% sure if this is exactly here. But what is behind it, I want to construct it via a geometric construction which uses fixed points under C star torus action, and this is an endomorphism. So here's the setup. K is algebraically closed field, and Z is the smoothest projective variety. With a C star action. With isolated fixed points. It's isolated finite and many fixed points. That's the setup. So of course there's basic examples. So the main example is I take a G mod P for reductive algebraic group. Of course I have the action of G on here. This contains the standard torus, or the choice of a maximal torus, and inside there I have any choice of C star given by one parameter subgroup. And so, in particular, I can take for G mod P the Grassmannian, which we had in just the last talk. Yeah, and if I would take the full torus, then the torus fixed points in here are exactly the coordinate subspaces. If I take a Grassmannian and take a good choice of C star, so a regular co-character, then the subspaces are again coordinate subspaces, and so we can label them also by, say, the partitions fitting into a certain box of size, whatever. Dimension of the subspace times the coordination. Okay, good. So this is all standard stuff. So let me mention two more things of examples. So Springer fibers. So these are, I take G mod P, and inside there I take fixed points under nilpotent element. So these are Springer fibers, or most general for P Spaltenstrand varieties. So these are in general not smooth, but still things like this will come up. They have a C star action.
What is the exponent?
So X is the nilpotent element in G, and I take just flags which are fixed by this nilpotent. Again?
What does nilpotent mean?
Oh, so take as an example GLN, then nilpotent is just a nilpotent matrix. If you take a classical group, you can embed it into a GLN, and then it's still nilpotent, and otherwise you have to take the adjoint substation.
Nilpotent as an element in the Lie algebra.
As an element in the.
So you don't mean unipotent?
Okay, you can take unipotent, and then this is really fixed. If you take nilpotent, then X of a flag space has to go one down.
Oh, all right.
Sorry, I mislocated this. Yeah. Okay. Good. So a special case are the Kleinian singularities, or if you want ADE singularities. So I just draw the picture in type AN, so you have just glued together spheres like this, S2 or P1. And so this is the case where this X is nilpotent with one Jordan block, and then with two Jordan blocks, one is of size 1 and the other is size. So, and in this case, I just draw already the torus fixed point, the C star fixed points. So one sees here that these points turn out to be the C star fixed points. Okay, good. Right. So now, what I do, I want to do more series. So first, I take the collection of fixed points. Then I take C plus, this is for me the attractor variety, and C minus, this is repeller. Well, you want to see the abstract here? I think that's what people do here, or some people do here. So these are varieties which represent the following factors. So the first one represents just coming from S to Z. C star is so S is now any speed is the triple C star. And what is this attractor? This attractor is given by homing from an A1, which is equal to plus times S times B. That is A1 plus is just A1, but with the action, so lambda acts on X just by multiplication with lambda, and then I can of course do the same thing with Z minus, and I take here A minus 1 And the minus is just, so when I put the minus, then I just invert this. So, and then in concrete term, I just ask the question, given a fixed point, which points of my variety are attracted to this point? So I take the action of lambda acting on x, and I take the limit. So I take the limit of lambda going to 0, and I ask which points go here to a fixed point. And this is the attracting cell for the thing. And so elements in here consist out of two things, a fixed point plus an element in this attracting cell. Okay, so in this example here, I have these fixed points, and one can show that what is attracted to this fixed point, with the correct normalization, is exactly this sphere. What is connected to the second one is the second sphere, etc. And the last one has as an attracting cell only this point. Okay, good. So now I have a picture Z. So this is the fixed point inside Z plus, inside let's say minus, just the normal inclusion. And I have also the map in the opposite direction, which takes corresponding fixed points for an attracting point. And then this lives inside Z, modular P plus P. Okay? And so what we get from this attracting cell is just some kind of decomposition of the variety in say attracting cell plus or repelling cells, where I run over fixed points. So I run over fixed points, and in here it's exactly everything which is attracted to this. Okay, so now what I want to have is a general construction. A general construction of an algebra structure on things connected to this. So what we can do is, the first thing one can do is one can take such an attracting cell and take the closure X and another one or Y, and I can take the cohomology, maybe with compact support, depending on where I am. Or I can also take things like Z plus X intersected Z minus Y. No, this is okay. So maybe let me write it like this, without the index. Something like this, so which is the direct sum of X and Y, the attracting cell to X, the attracting cell to Y, and here this is the direct sum X, Y, repelling to X, to Y, and I take so what I can do is I can take the fiber product over these things over Z and the fiber product of these two things over Z, which in concrete term is just the pairwise intersection of two of these attracting cells, or one repelling and one attracting, and I sum of all. And I hope you see already that this looks very much like the stuff above. So now what I want to do is I want to understand.
Why does it look a lot like the stuff above? Sorry.
I mean, it's just a kind of thing. At least I have a vector space, which is a direct sum of things of pairs of X and Y. And if I'm lucky and construct an algebra structure, I'm hoping that in this way I can describe the things which I really want to describe. Okay, so
is it also obviously an exceptional sequence in the same sense as well?
no, no, nothing is obvious here, I think, at the moment. So, let me...
It was obvious just a minute ago.
Okay, what is obvious is that I have a vector space, that's obvious. Which is a direct sum over pairs, that's obvious. What is not obvious is that there is an algebra structure, and it's not obvious that this has anything to do with the concrete algebra.
But
X and Y are running through.
So, X and Y are running through the fixed points. So it's a finite sum for me.
Is there correspondence between that and some
Yes,
weights or
so
something?
let me do an example to give you a concrete. So if I take the example of flat varieties of magnets, then these things, so without the bar, these are just the usual Schubert cells, and with the bars, these are the Schubert varieties. So intersection of Schubert varieties. And this is usually a very terrible thing. And what is this in the flat variety case? This in the flat variety case is also something very famous. So it's an intersection of an open pre-Hausdorff with the opposite open pre-Hausdorff. So this is what people call Richardson varieties. So respectively Richardson varieties. And so for me, Richardson varieties are now special examples of what people introduced just recently, braid varieties, where in particular the coordinate ring is interesting because there's cluster structure. Also braid varieties and Schubert varieties are very interesting in connection of categorifying not to this sort of categorification business. Okay, so now I want to explain a little bit where we get an algebra structure from this kind of things and how it's connected to them. So what I want to have for this is a general setup. So I call it by d of c. So this is any A1 invariant formalism of sheaves. On set with a 6-func performance. So this could be, for instance, constructivism. Say over complex numbers, or this can be Arabic. It can be coherent shapes. Mixed motives, or whatever.
How coherent sheaves A1 and that? Coherent sheaves, why are they A1 and that?
So I mean, I don't say that. So I want to have a derived category of some coherent sheaves where I have a C star action, and I want to only consider a subcategory of sheaves which is in there. And it could be whatever. Yeah. Just pick something where you feel comfortable in. That's fine. So now I define something which is the analog of this Lohmann modus upstairs. So I take an object which I call delta, like delta for highest rate categories, and it's defined as follows. I take Q. This is for me the constant sheaf on this Z0. So if you want, you can take a constant sheaf of one fixed point extended by 0 and just take the collection of them. I denote by Q the just direct sum of them. So I can use my Q plus from here and pull it back from a sheaf from here to a sheaf to here, and then push it forward via this P. So I get at the end the sheaf on Z, and this is what I call the, so this is the V of Z, and this is what I call the standard sheaf, or standard object. And if I, for instance, choose here the category of pure sheaves on flat varieties, or the category of constructible sheaves on flat varieties, and I do this construction, I get exactly the analog of Lohmann modules under this Riemann-Weber constants. Yeah? So, and here's the theorem, the first theorem.
So, may I ask you, so you have a set star action everywhere, or?
I have a C star action on my big set.
On your, okay.
Yeah.
So that's what you mean by A1 invariant.
No, I mean, so the question of what are equivariant sheaves in the divided sense is, I think, not something totally trivial. And I just want to have this kind of, yeah, I can say what is an A1 equivariant sheaf. I mean, in the sense of, what do we want? Don't and don't, for instance.
Okay.
Okay. So theorem, so this is theorem with Jens Eberhard. First statement is when I have this set up and I want to compute harms from delta to delta, so this is now the analog of the direct sum of all these Wermers upstairs, then this is isomorphic to cohomology of compact support of Z minus this Z plus final product over Z. So it's exactly this power is intersection of cohomology of Richardson as a vector space. As graded vector space. But I put the graded in brackets because for this one it's only graded here, which I don't want to do. Yeah?
What is Q plus?
Q plus, this is this. Oh, sorry, I didn't draw the arrow. It's I have a map, so here in here I have a point, a fixed point plus an attracted point which is attracted to, and I can just forget the second thing. Okay, so this is as isomorphism, and this is already, I mean, this cohomology with compact support is already something interesting if you are interested in group cohomology. So if you try to compute this cohomology of a Richardson variety using the pre-hard decomposition, you compute in small examples, for instance, the cohomology of the group G and N. This is compact support. Second thing is, there is a, I would say, non-trivial description of the algebra structure. So here on here I have an obvious algebra structure in terms of the convolution products. So it's what one might expect this way. But let me make a few remarks about this. So as a special case, this is this Werner modulus, and I plug in the black variety. And in this case, this isomorphism of vector spaces, this is a theorem of Searle-Riche and Williamson. But they did it really by hand. So they didn't have any sort of conceptual setup like this. They just computed by hand x between Wermers, and they realized all this. And this also, I mean, everything works also in positive characteristic. So why this is not trivial, the algebra or the multiplication using this convolution product uses an interpolation variety, and which is called the Trinfeld Gale-Screen interpolation space. So this is, I mean, maybe this is expected when Gates will prove such a result. So it's a really cool construction, but it's a very hard space. And it's not very concrete, but so it interpolates between Z and a tubular neighborhood of Z0. And one can use this to describe this algebra structure. But it's impossible to compute anything. It's totally impossible. So, and the technical tool, which somehow gives an explanation why this theorem should hold, is an interesting result from Braden. And what is behind this is on the right hand side, one has this Z minus and the Z plus, so it's a mix of minus and plus, whereas in the definition of the delta, I made a choice and took the plus versions. So I could also take the minus versions, which would give a similar result, but I made a choice, and so the right-hand side is somehow a bit surprising that this mix comes up. But the explanation is the main technical tool is hyperbolic localization. And this goes back to Braden, I think. And it says there's an equivalence of categories. Between an immediacy, namely the corresponding category of sheaves on Z0 and the subcategory of sheaves on Z. So, and the equivalence is given by the following factors. I can take this P plus shrink and the Q plus star. So important here is two pluses. So I only take the plus attracting cells. But I can also choose the minus. And I can do that. And so these two factors are the same, and they define this equivalence. And this is the full subcategory of these cells of C star equivalent monotonic sheaves. So this looks very fancy, but it's in fact something extremely easy. So maybe I can take my action of C star. So I have my action at A. But I also have a second map going from here to here, namely the projection onto the second coordinate. And what I just want, I want to only consider sheaves where the A star of this sheaf equals to projection T star. And this is what is going on. So it's compatible. So nothing fancy.
So it's sort of like Smith's theory.
Exactly, yes. Okay, and the last remark I want to make, maybe for this audience, is there is also a DT version of this, or an infinity category version of this, of the theorem. And so when I just replace this by infinity categories, I can look at the mapping space from delta to delta. The mapping space. And so this is on the other side, I have this Z minus 5 over 7 Z plus, and I can take here, right. So this is the complex of compactly supported quotients. So I just mentioned this because I just want to say, whatever setup you are, I think this construction works. Okay, so this construction works and it is fine, but it's not helpful for people like the complete descriptions. And so I want to do a complete example. I look at the category of Hilbert sheaves on the Grossmanian before and the corresponding derived category. So I take the normal action of the torus and like that before. So in this case, I have 6 C star systems for regular C star action, namely given by EI EJ subspace, where these are just the standard bases of standard basis elements of C. So the coordinate subspaces are just the 6 possible choices of choosing 2 basis vectors, and then I just want to draw the corresponding curve, give you an idea what comes out. So the curve looks like this. So I have my 6 point, 1, 2, 3, 4, 5, 6, and then between each of them I have two kinds of, if I have a connection, I have two kinds of arrows. So that this one is home, and this one is next one.
So your T of per is everything C star at the letter end, or just
Oh yeah. Everything is starting. Right, and then I don't know if maybe I don't write them down. We have an explicit relations. So this was done by a student of mine on the left hand. Okay. So now, in case of flat multis, I want to briefly say how we might can make this very explicit, this multiplication. So the multiplication can be made explicit.
So there is no dotted out if there's one vertex where you don't have it dotted out.
Oh, no. Sorry. You are too clever. So multiplication can be made explicit in these cases. So let me just briefly explain this. So this is using parameterization of Z plus W via uniform matrices. So this UW plus, we can identify with unipotent matrices. So in Lustig's notation, this is UW. So it's a subgroup of unipotent matrices depending on my torus fixed point W, which I label by a Y group element. And so I have an isomorphism like this, and this works for the positive unipotent and for the negative unipotent. That's a standard way how to, for instance, regress many case how you write down cells. And so what we can do, then we can do the positive part and the negative part, or the negative part and the positive part, and define the corresponding map just by multiplication. So U bar goes to U bar WP over P. So and the statement is they have the same image. And using this, one can do a concrete combination so that V be the union of all these images over all fixed points, on the labels of the fixed points. And then one can do the following. So if I want to have a product from here times here to here, what I can just do, I can put on top the C minus times V times C plus. So I have a map, an obvious map like this, because the V goes to here and it goes to here, via this map there. And I have an obvious map to here, because this is the same as C minus 5 over W C over C. So I just typically write this in the middle. And then I can do this correspondence, and this gives me my difference. So the conjecture is convolution along this diagram and gives the above multiplication, abstract multiplication, and the theorem is this is true in the corresponding case. But we have almost a proof, but Yeah, there's a technical thing which always us. So why is the Grassmannian case easier than the rest? It's easier because these uniform groups commute with each other, and so there's no difference between this way. Okay, right. So, but the warning is the A infinity algebra, which is behind this, namely this X algebra, has a higher magnification. So this is also something which was proven by the time. Okay, so and what we have in progress is an explicit.
Why is it a warning? Isn't that somewhat expected from the
Okay, for you maybe it's not a warning, for you it's maybe the normal way thing. For me, this is a warning because most of the time when we do geometric representation theory, we look at like simple objects, simple double sheets or something, and we prove very quickly a formality result. And so the warning is for me that these Wörmer modules behave very, very different from all these other things which one usually looks at in geometric representation. But it's not unexpected, of course. And so what I wanted to say with also
Not a warning, it's a teaser for something good.
Yes. So and in this work there is explicit higher multiplications constructed. So an in progress is an explicit DG model. Based on so-called Deodat cells, which are a non-trivial decomposition of this Richardson model. Okay, so now I want to, because I said I wanted to connect it with Fukaya categories, I want to give you a slight glimpse how we write down this DG algebra at the end. And this comes from it's given by some diagrammatics. And I mean, many people say I'm a combinatorialist, but I'm not really a combinatorialist in the sense that I'm only interested in combinatorics. But I'm interested in the way that combinatorics in a way so that I can see the geometry. And this is what these diagrammatics which I write down are supposed to do. And the pictures are motivated for me from Fukaya categories which exist, where these X algebras are supposed to arise, or where we know that they arise as X algebras or endomorphism algebras in some Fukaya cycle category in certain objects. Okay, now let me draw these pictures. In just one example, there's many people. Okay, so delta x, which is one of smaller x. So this is corresponding to a Wörmer model. In the category O picture, there's a category O. So this is represented, or this is in bijection. The fixed points are in bijection to the span of two basis vectors, the I and j, and so I and j are between 1 and 2. So when I draw them as lines. So, for instance, I have 4 points. I might draw this line for taking the third and the fourth basis vector, and I draw this line for the first and the fourth, and I draw this thing for the second. Okay? So it's just a picture for doing this. So now, I want to compute the space X from the corresponding delta x to delta y. Okay? So what I do now, I have an x and I have a y, and I do a clever thing, which people who know Fukaya calculus might recognize. So I have this x, say this one, and I have a y, and I draw the y also, but I will move it to the left. For instance, something like this. Okay, so this gives you pictures of for each pair of two such standard objects labeled by a fixed point. I have such a picture. And now a basis, so that the statement is the basis of this x correspond to configurations of intersection points exactly one per line. So what do I mean by this? So here is an intersection point, right? Here is an intersection point. Here are intersection points. And so, for instance, when I choose these two intersection points, I have every line has exactly one point. If I do this one, then I'm in trouble because this line, I cannot do this, right? So this is impossible. So that means between these two guys, I would have no x. Here, this is also impossible because this is to the left of everything else. So this guy doesn't intersect anything. So the fact that this is to the left and it doesn't intersect anything, this is connected with the exceptional sequence element. So this is also impossible. Okay, what we have then is we have the possibilities of such a thing. Let me put this intersection point here. So this has priority. We always do this when this is possible. And then we have these kind of points. And for this kind of points, I take two possible symbols, which I call which I want to somehow allow. This symbol and another symbol. So what this corresponds to the homology with contact support of a point. And this corresponds to the homology with contact support of a C star, which is two-dimensional. So the claim is when one draws these pictures on here, we get a diagrammatic description of the basis of the sense. And this C star and the point, they come exactly from this Deodar decomposition of these writers. And there's also there's also an indication how many lines are before I need something. If I put this also into account, I can even see the sort of additional grading, which we often want to use, which comes from some mixed Hodge grading. So everything is important. Okay, good. Right. So now, I said everything is motivated by Fukaya families. By where are the Fukaya categories? So I definitely don't want to define what Fukaya categories are, but let me explain a little bit. So here's the example. You take the Tasmanian Pn. So, and this is G mod P, and P is parabolic. And on the other side, we have the Springer filter, G mod P, X, where X is the nilpotent, standard nilpotent for example. Okay. So, and here there is the slogan, which I have for many years, but I can only prove some of it. So Perver sheaves on G mod P is cosine two coherent sheaves on something related to G mod P X or the Sloterdijk slice of X. So X is an important element. I can take its corresponding orbit and a slice to it in the corresponding the algebra. So this is a slogan, and here is a theorem. And that's the old theorem.
But you mean for those sheets on G mod P?
Ah, sorry. Yes. Yeah. Okay. And so, for instance, combinatorially, one knows many things about this, but one would like to have a precise theorem. And so if you look at the literature, many things were done here, and many things were done by Retsukovnikov in particular on this side. And they look very similar, but there's no precise statement about this, except of.
So in the case of T is equal to B, does this simplify that?
No.
No, okay.
No, it becomes harder. So I come to the other side. This is the simplified one. Yeah. So when I take the Grassmanni case, then there's an equivalence to what. So this is an abelian category, whether she's on that, or one parabolic category. There's an equivalence of abelian category to something which is the T structure, in the sense of Retsukovnikov for the exotic T structure, on the compactification of a resolution of the following class. So that's a precise statement. Clear? Part, yes. So half. Yes, sorry, yes, of course, the half. Yes. And so, why do I call it a coso-duality? So when I take a projective, they are sent to symbols. Yeah? And so this way it's a coso-duality. So now, and this on that side, people did, so connected with Sloterdijk slices and important orbits, people constructed Fukaya categories, in particular this Sider-Smith Fukaya category. So let me just connect this. So concrete for this X being such a case. So two nilpotent blocks, two blocks for the nilpotent. Then this Sloterdijk slice, Sx, and this compactification of the resolution, this I call Sx bar. Right? So this Sx bar is equal to flags of length L, but sitting inside a 2n-dimensional space, such that X preserves. So what I have is something like a string of fiber, but I don't fix the last space. And this has the advantage that it becomes smooth. And also, this is a smooth symplectic. It can be viewed as a symplectic writing. Okay, and this is where Fukaya category people can work on. And now let me just do a stupid trick. So inside there, I have the string of fiber. Namely, I just set this to be C to the N. This is by definition the string of fiber. And inside the string of fiber, I have the closures of these attracting cells, each time. So, and inside there, I have so this is of maximal possible dimension. So, and Springer proved that the Springer variety is equidimensional. So that means there is the irreducible components have all the same dimension. And the claim is that if I take these attracting cells, the closure of it, and I take the ones of maximal possible dimension, these are exactly the irreducible components. And they sit inside. And they have the half dimension. So these have half dimension of the space. So what I have for free is something which I can call a Lagrangian inside here. Okay? And what I let me finish by doing this, and I'll just write down the last word. So maybe I illustrate this in the example upstairs, which we had at the beginning, these Kleinian singularities. In this Kleinian singularities case, we had attracting cells for this torus fixed point, or this star fixed points. Most of them were just P1s or S2s, whatever you want to say, and one of them was a point. And so I want to just take the big ones, the spheres that we saw, and I ignore the point. These are then the irreducible components in this Kleinian singularity picture. And they all have the same dimension. And so the theorem is now, here's the definition. The algebra geometric Fukaya as objects, and it can also be extended. As objects, the irreducible components, the Springer fiber, respectively all. So this W is in the smaller set, and this is in the big set. And it's not zero. So I take either maximum ones or all of them. Extended is when I take all. The maximum ones are just a thing, and then morphisms are just so from Z bar plus to point plus, either in this or the other version, are just homology, if you want, with compact support, but we don't need this in this case, of the intersection of it. So that's the definition, that's a nice category, and the theorem, which I conjectured, and then it was, and the composition is convolution. The obvious convolution.
So what is that? Here is an any space with this direction or specific. So what is that?
So that is the one upstairs, the specific one. And so the theorem is, now I have to check, so this is Hausdorff. This algebra geometric Fukaya category is equivalent to the Hausdorff category. So the proper Hausdorff Fukaya category associated to SS bar. So that's a statement. And so in this world, one also has analogs of normal models, these are called limbus. They have no idea how to compute the X or flow homology between them. But I just copied their picture, and these are the pictures I draw upstairs. And I can prove that this is the dimension of the X algebra. And just have complicated things like that, I have here two intersection points of this one. I have here intersection points like this, which somehow are bounding a little square. Whenever such a square comes, a differential comes in to have the proper DG algebra. And so what we hope, we are writing down on the last bits, that we can really write on a very explicit model for this DG algebra, for this exponential boundary space. This explicit basis built on this, based on these diagrams, which are then supposed to really compute Flair homology between simples in this Fukaya algebra. But I think that's okay. Thanks.